So I am joined on the podcast by Kelvin Long, who's a fellow of the British Interplanetary Society, and currently is. Are you represent the Interstellar Studies? Is that correct?
The Interstellar Research Centre.
The Interstellar Research Centre. Okay, so yes, who represents the Interstellar Research Centre and has been involved with lots and lots of various different space-related institutions and others outside of that. A bit of a polymath. Welcome to the show, Kelvin. How are you?
I'm good, thanks. Yes, like everyone else on lockdown, so enjoying the sunshine there.
Yeah, so I'm assuming you're enjoying lockdown a little bit because you're a prolific writer and you like to get down to studying stuff.
Yeah, that's for sure. I work from home, so it's pretty helpful to have my office at home. However, I also have two small children, so they're very distracting, and I have to lock the door. But I'm managing to get a few papers written and trying to get some books progressed. So that's helpful.
Yeah, I think most people know you as a Interstellar guy. So let's start the conversation about interstellar travel, because who was your inspiration, and why did you get into researching interstellar travel?
It's an interesting question. I mean, my own journey in space, interest in space, goes back to when I was 14. I went into a museum in the Potteries in Stoke-on-Trent and saw an Apollo exhibit. So that started my interest in space. Jumping to Interstellar, I think really happened from two angles. The first was when I was doing astrophysics masters at Queen Mary College. I met Martin Fogg, and he was a prolific author and pioneer of exoplanet sort of modelling and free floating planets and so forth, and wrote the very first book on terraforming of Mars. And he introduced me to the British Interplanetary Society. Of course, once I discovered the BIS, I then began to learn about Project Daedalus and meet Alan Bond and some of the others, Bob Parkinson, Gary Webb from the Daedalus team. And that really got me to think about that whole field of interstellar and how different it was to interplanetary exploration. In particular, I was interested in doing some projects, but I was quite young at the time. So my first entrance was, I'd done general relativity at university. We'd studied black holes and cosmology. And so I started jumping into warp drive metrics because that was applications of GR. First appeared in the field in 1994, Miguel Cubier. And but after spending a couple of years on warp drive, realizing that it just breaks so many laws of physics and it's very difficult to try and build a warp drive, I got a bit more practical, and that's where the kind of genesis of the idea of Project Icarus came about. And what I observed was, when I was looking at the interstellar community, there wasn't really a lot going on at the time. There was a couple of organizations that were sort of existing. The Tau Zero Foundation was the main one, run by Mark Millis, United States. He used to work for NASA. And but they weren't really doing much, and the BIS itself wasn't really doing much in interstellar studies. So, and a lot of the people that have pioneered the field had either passed away or moved on. Recently, we just lost Freeman Dyson, who was one of the other pioneers in the field, who I also knew. I really wanted to get some activity going in interstellar to really pick up the energy in the field, and then think about building a collective community that focuses on the stars. And this was serendipitous because, of course, at the time, we started to get the exoplanet discoveries. We started to find the first evidence of planets around other stars. Of course, now I forget what the number is, but we must be over 3,000. So once you have planets, then the question is, well, how can we get there? That's not to say that the only purpose of exploring space is to go to planets, but certainly that is an interesting factor. And my journey really started from that, and I've been involved with lots of different interstellar organizations since, either co-founding them, founding them, or helping other organizations. And it's been an up and down emotional journey, I must say, but it's been very interesting. And I feel a bit like Thor Heyerdahl on the raft when he's trying to cross the Pacific to get to the Pacific Islands, Polynesian Islands. And I feel like I didn't quite make the island. Like I crash landed somewhere, but I'm not quite where I want to be yet. And I look around me at what's going on in the field, and there's a lot of good work doing, but I still feel we're not quite going in the right direction to bring interstellar studies into the mainstream. And given that, the things we're thinking about at the moment, such as the pandemic, which has really gripped the world, I think that it's more important to have a long-term vision that goes beyond just what we're doing tomorrow or next year, or even in 100 years. Where do we want to be as a species in hundreds of years from now? And so I think Interstellar has a role to play in that.
Yeah, actually, I couldn't agree more. I was listening to Anne Druyan, who was Carl Sagan's wife, pretty much saying exactly that sentiment about that we need a map for the future. We need to decide what we want to do in the future so that we can actually draw a map to get there. And obviously something like interstellar travel is such an interesting concept. I mean, before we go on to kind of the specifics of interstellar travel, would it be good? I mean, it'd be really good to outline the real problems of interstellar travel. What, kind of the key points of why it's so difficult.
Yeah, that's a good question, actually. Unfortunately, I mean, I love science fiction. I've got an enormous science fiction collection. I should have mentioned, when you're talking about who influenced me, Arthur C. Clarke was one of the big influences on me. I read all of his books. And many of them featured star drives. So that got to be interesting in the technology. I think the problem with science fiction is it makes it look easy. It's a bit different with Clarke because he actually included some of the physics and engineering in his design, such as the Discovery 2 in 2001. But suddenly Star Trek, Gene Roddenberry, which, there's a beautiful book, The Making of Star Trek, where he describes his requirement for the Starship, where he didn't want it to have any engines or anything like that, or fire coming out the back. So that's really created our perceptions of what going to the stars would be like, FTL travel. And so with Star Wars, those are the two big sort of poles in the tent in science fiction films, at least. And unfortunately, it's not quite like the sound barrier. I mean, the sound barrier, which was broken in 1947, 14th of October by Chuck Yeager, that's a very different phenomenon. But I think people tend to think that the speed of light is just another barrier that can be broken. But there are fundamental reasons in physics why we can't go faster than the speed of light. However, there is an opening there because Einstein's physics tells us that actually space itself can go faster than the speed of light. It's called superluminal, and that's in fact what happened at the Big Bang expansion, superluminal expansion of space. And so, but when we actually get to the nuts and bolts of technology, like the Voyager probes, how difficult was it? With 1977, we sent those Voyager probes, and they were only at 130, 140 AU. The nearest stars are sort of 240, 50,000 AUs away, Proxima Centauri, Alpha Centauri stars. So in order to get there in, say, even a century, you would have to travel at something like 2,500 AU per year, an AU being the mean distance between the Earth and the Sun. The Voyager probes are traveling at something like 3.5 AU per year. So several orders of magnitude in scale. If the velocity is several orders of magnitude in scale, that implies also for the power systems, they have to be, instead of just multiple hundreds of watts, which is what something like the Voyager probes would use, which run out in 2025 because the power degrades, you would need something else to power the system, maybe a much bigger nuclear reactor. And it also has other problems like communication problems, because now you're communicating over much longer distances. When you look at something like energetic reactions like Daedalus, designed by the Daedalus team, Alan Bond and so forth, this was using fusion fuel. And you actually look at the numbers that's required to push something like that to the stars, and it comes out something like 40 megawatts per kilogram, which is just phenomenal. And we're talking about terawatts, jet powers. These are the sort of metrics we use in propulsion terminology. And this is just, when I give talks at NASA, for example, and I've spoken to all of the NASA laboratories, I always make sure I give these numbers because it's my way of saying to them, look, I know it's really hard. I'm not up here pretending that we can build a Starship tomorrow. I know that when you run the numbers, it looks very problematic. And I never say impossible, I just say problematic. However, when you look at the advances that have happened in the last few decades, I think it's certainly the case. We can't no longer say it's impossible. Nobody can say that. And as you know, there's a project Starshot, which perhaps we'll get on to talk about later, which is an active project at the moment to actually send something out there. So I remain optimistic that over this century, and my personal goal has always been to work towards, before 2100 launch date, is that we will be sending our first starships towards the nearest stars. But, you know, if we take that Polynesian model again, as Freeman Dyson used to refer to, there's other things in between. You know, there's the rest of the planets in our solar system. There's possibly brown dwarfs or other dwarf planets that are out there, free-floating planets which we can explore, the Oort cloud, the Kuiper belt. So these are precursor missions which we also need to be launching along the way.
Yeah, so in terms of the most promising near goal interstellar travel, would you say that is something like the Starshot type of propulsion?
Yeah, so Starshot, as you know, is a directed energy beaming method. We'll talk about the specifics of the technology perhaps a bit later, but and it's currently costed to be of order, I think it's 10 billion, the last number I saw, to actually launch the first flight of a gram scale probe. So this thing is grams in mass. But actually, there's other projects underway. I've been involved for the last couple of years with Johns Hopkins Applied Physics Laboratory on a 1000 AU mission. Originally, there was a proposal in the 1990s from JPL for a 1000 AU mission, and that unfortunately didn't go anywhere. That was called TAU, 1000 Astronomical Unit mission. But the Johns Hopkins people were trying to resurrect this idea. And certainly, I mean, the idea of, we used to talk about 200 AUs, but given that the Voyagers are effectively there philosophically, you know, they're sort of they're at 140 AU-ish. So what's the scientific advantage to sending something to only 200 AU? Okay, so you're taking measurements of the same particle populations, charged particles, the plasma and helium sheath and so forth, which is very good because it helps you to understand your data a bit better. And we want to understand better the structure of the heliosphere bubble. But really, we want to know what's beyond that, what's outside that heliosphere bubble, what's in the Oort cloud. And 1000 AU is just a good number to try and go for. And certainly technologically, if we wanted to send one, if let's say we had a program to launch one within a few years' time, and it was government funded or privately funded, and there was a decent budget of already billions to do it, we could certainly launch that. We know how to do it today. It's just really, it's not necessarily about the propulsion system, it's more about the payload, what you actually want to send. And this is one of the issues with Project Starshot, of course, because Project Starshot is so small in mass, gram scale. The question is, what sort of payload can you fit on that, because it's so tiny? And what's the value of the science you're doing? And therefore, does it justify the economics?
Well, yeah, can you describe, even though the propulsion is important, can you describe in a little bit more detail that 1000 AU mission, what it actually looks like, or is that something that's not really pieced together, you've just got some numbers, or is there a specific
So there's no design at the moment, but what there is they're basing it on the Pluto New Horizons idea as a reference. So it's something like a 30 watts per 30 kilograms mission. So it's something like a New Horizons, so maybe 500 kilograms in total mass that you would send out to 1000 AU. So it would maybe do a flyby of one of the other, either one of the planets or one of the dwarf planets like Eris or Ceres, or there's speculation that there's an object that's much further out, there's Planet X. So could we do some astronomical observations of that? And suddenly, in terms of justifying it, we only have to look at the images we had of Pluto, even from the Hubble Space Telescope, which has been a fantastic achievement. And you compare that to the images that New Horizons has taken of Pluto. And they're just not comparable. I mean, and it really does justify why we need to send probes. I wrote a paper on this recently, published in JBIS, presented at the IAC in Bremen last year, I think it was, a year before, and arguing that, there is an argument for why we should be sending probes and not just building big interferometers. But certainly 1000 EU is a good target distance, and there's people been working on this idea for years. Ralph McNutt, Cloud and Ricconi have really been trying to push this mission. I would love to see the European Space Agency or NASA collaborate together to get behind such a mission, because it is viable today.
Yeah, it'd be good to see the Chinese and the Americans do something like that, I guess, because you kind of get to think that the two of them should be able to get the resources for something like that. But you're talking, wait, I just got to check that I haven't dropped out here. Yes, but you're talking. Obviously, when you start talking in billions of dollars, and particularly when it gets to tens of billions of dollars, you're talking about you have a choice between something like the James Webb Telescope and a 500 kilogram probe out to the outer solar system. So, how do you weigh up the science that's gained by each?
Well, I mean, in the United States, they have the decadal surveys, which is every 10 years they review what the science objectives are as national priorities. So that includes sort of galactic and planetary and heliospheric. Now currently, the Johns Hopkins study is a heliospheric decadal proposal. So its main focus is on the plasma sheath, understanding the solar heliosphere. But it's an interesting one because you can also do some planetary science along the way, which, is you would end up having planetary scientists involved in that. So I do think it has to be driven by the science. But, there's also an argument for getting out there and just seeing what's out there and making discoveries with things we didn't even know existed. I mean, building a space telescope like Hubble or James Webb, and I've been to Goddard and I saw James Webb telescope being tested when it was there in the huge satellite sort of clean room. Also, I was lucky enough to see the solar probe being thermally tested in the vacuum chamber at Goddard at the same time, which is really cool because myself and my family's names all on that probe, so that's good to see that. I think you do have to do, a comparison of the science benefits and then justify the costs. I don't think it's reasonable to just spend enormous amounts on something that doesn't give good science return. Having said that, Breakthrough Starshot, which is at the moment a completely privately financed initiative. There's 100 million at the moment been allocated, and Stephen Hawking was the sort of chief scientist on the board before he passed away for this project, and I'm on the advisory committee for Starshot. That's being led by Pete Worden, who's a former NASA Ames director, and also Yuri Milner, who's the sponsor. And that is privately financed, and it's, as I say, 100 million R&D money at the moment for the first sort of 6-7 years. And that's making really good progress. Lots of good papers coming out, lots of universities involved in doing experiments. And hopefully that will move forward towards a full-scale launch at some point, maybe a precursor probe, a test mission, maybe around the moon and back or something, using laser beam technology. Sometimes it takes private financing to do these things. I mean, just look at Elon Musk and SpaceX, what they're doing, which will have, with the reusable rockets, will have a revolutionary effect on the rest of the launch industry. Because what would it take to get the rest of the launch industry to look at those reusable rockets? So if he brings the cost down to, I don't know, $1,000 per kilogram or something eventually, which is also what, SSTO was attempting to do with Skylon in Britain. This will have radical effects on the rest of the launch industry, which also means it's now cheaper to put telescopes in orbit. It's also cheaper to launch space probes. So it has an effect on the whole system. I know Alan Bond's view has always been that you have to break that bottleneck. You have to bring that launch cost down first, because mass scale exploration of space is not going to happen unless you can do that. Yeah,
I mean, Musk has been talking about $300 per kilogram for Starship. So that which is better than the space elevator. So yeah. so that'd be pretty phenomenal. But
one thing we should say is that although the name is kind of called Starship, it's definitely not a starship.
No.
by any definition, it's not a starship. But who am I to question Elon Musk's naming rights? So.
No, but I suppose it may facilitate starships. I guess, but like you said, because it changes the paradigm, doesn't it, of actually getting things out of Earth's gravity well, which is one of the sort of big points. Now, while you were talking there, I was thinking about this. Just the propulsion of Starshot, where you've got a laser that's pushing something to relativistic speeds. there is a connection, isn't there, between interstellar flight and looking at it, because the energy is so massive. That's what's required. That you essentially will always build something that becomes extremely dangerous. And when I say extremely dangerous, as in it becomes a weapon of mass destruction. How do you ever get round that particular sort of problem? Because I can see with Starshot, when it actually comes to interstellar missions, you're going to need laser banks that can be obviously used for nefarious lots of other ways you can use it, and it become dangerous.
Yeah, you're right. I mean, I think it was Heinlein, the science fiction author, who said something like any advanced propulsion system can be turned into a weapon. And it is true. I mean, even Daedalus, Alan Bond used to say, you could never look at the Daedalus engine because it's so luminous and so intense, it would just blind you. And never mind being in front of it. I mean, you couldn't launch it from Earth orbit, which is why they launched it from one of the moons of Saturn, theoretically. So Starshot has the same problem. It's directed energy. Of course, the US has a long history with Star Wars program under President Reagan and so forth. And well, I mean, if you look at the original proposals for directed energy propulsion, which really came out of Robert Forward, who was a brilliant American physicist who unfortunately died. But he did such amazing work. He was on a quest to find propellantless travel. So he was looking at antimatter to start with, because that is much more efficient compared to, say, fusion. But then he started to look at SALs, and then he started to look at lasers, and then also microwave beams, masers. And he really pushed the field. He even presented a paper, I think in 1976, to the US Congress, saying that we could build a program. And they said, when could we launch the first mission to the stars using this project? And he said around the year 2000. So he was very optimistic. And this was something like a 1 tons probe called Star Wisp. But his architecture was based in Earth orbit. So it was using these massive Fresnel lenses to reconverge the beam, because the beams will tend to diverge. Something called Raleigh's law. And so you have to recollimate the beam, because once the beam starts to diverge, you no longer have full pressure on your surface. So he would build these massive Fresnel lenses, like 500,000 tons in orbit. So that's an enormous scale project. Then you have a laser which gets light from the sun, pushes this SAL, reconverges this beam, and then pushes on a 1 ton SAL that's maybe, I forget the dimensions of it, maybe 10 kilometers across or something, and it pushes it to the stars. But in principle, I mean, if you look at the Gerald and Hill studies in the 1970s as well, they were talking about getting solar power from the sun. So similarly, you could use that same architecture to power the national grid or to push satellites. But you're right, you could also turn it on an enemy country and take out an enemy country. So I think the complications with these issues is one of the reasons that Project Starshot controversially decided to not go for space-based launch. So their architecture is to have ground-based beaming. So you'd have an enormous array of beamers on the ground, generating something like 100 to 200 gigawatts of power, beamed up to a spacecraft in orbit, which has a SAL which is only about 3 meters across, carrying a gram-scale payload. And in theory, you could shoot people's satellites down, but it would be difficult to, fire that laser at a country because it's on the ground. So that's one of the reasons I believe they chose to do that. They've also gone out of their way to make Project Starshot international, because they believe that there needs to be understandings and conventions in place and protocols. When you would fire this thing, you would have equivalent of launch windows, just like rockets, they have launch windows. And those launch windows will be determined by whose satellite is in orbit right now above us, because you can't fire it if there's a satellite that's about to come over the horizon. So, and of course, with space getting very cluttered, that becomes more problematic, which means your window is probably going to get shorter. But, in the architecture, these things only fire for a very short time. You're talking about 5-10 minutes firing time. And they accelerate the probe to something like 10,000 G at 20% of the speed of light at 60,000 kilometers per second. So if you can find a 5 to 10 minute launch window, you could fire this thing. There's also the risk of, people attacking the architecture on the ground and trying to misuse it. terrorists, for example. So there's a whole bunch of security issues around this technology. And so it does probably require, in the same way that a project like CERN was international, or the International Space Station, by definition, is international, something like Breakthrough Starshot will probably be an international project. It may be that there are primary partners involved, such as the United States, which is primarily leading the project. But I don't see any reason why you wouldn't invite other countries in to be involved with it. And for them also to fire their own experiments, their own probes with their own technology. And that is really exciting, because now you allow for innovation in the probes themselves. You know, one of the things that justifies Project Starshot is continued miniaturization of electronics. And, you know, we're talking about launching this thing in maybe 20 years' time. And if microelectronics continues to follow a Moore's law, then who knows what we can fit in such a tiny package.
Yeah, well, there's plenty of room, isn't there, down there, as Feynman said. So, yeah, I'm just trying to think of the one thing that sticks in my head is this someone, I can't remember who said it, but it's, if you were to try and use conventional rock, just to give you a kind of, just to give people a kind of feel for how hard it is to get to another star. If you were to use conventional rockets, like if you were to use the space shuttle going flat out with chemical rockets, and it had to get to Proxima Centauri with just in a human lifetime, say 80 years, it had to get there. Conventional rockets, it would need a fuel tank the size of the observable universe. And I always think that says everything. It's just the amount of energy that's required to push you in a reasonable time frame, such unbelievably vast distances. It's just the vastness, isn't it, that's just mind-blowing and almost incomprehensible compared to even the size of the solar system, which in itself is incomprehensible. So with something like Starshot, when you send a small gram probe to try and get there with this enormous amount of energy, the first things that pop into my head is, how does the probe itself survive 10 minutes of this intense energy? And how does it survive the journey? Because it's not just empty space, is it? It's got to traverse space that's bound to have, I mean, anything of any size is going to rip that thing to tiny pieces. So how do you get around that?
Yeah, so just a quick comment on your other comment, first of all. The problem with chemical technologies, of course, is it's fundamentally limited to about 500 meters per second exhaust velocity, which is a fundamental restriction on its performance. Yes, so unfortunately, I've done a lot of work on particle bombardment. When I joined Project Starshot, my capacity is actually to be a member of the advisory team, which basically means don't do any work, just advise us and come to meetings, which is really fun. You know, great fun meetings, really good discussions, and we discuss all the sort of proposals that are being made and how we can move the project forward and so forth. But as a physicist, my nature is to do calculations. So I jumped into the particle bombardment issue because when the project was launched, Yuri Milner announced 19 sort of technical engineering and physics problems we needed to solve. And one of them is, you know, as this thing's flying through space, what's the erosion of it? And that erosion is really down to two factors. The first is dust itself. There's an enormous amount of dust out there. And the second is to charged particles. So hydrogen, helium, electrons, whatever else is out there. And so they all act to erode the structure. And they also potentially can be, you know, they can charge the structure and cause flip switching, as we know from conventional space missions. Instances have actually happened. If an electron gets inside of a microelectronic circuit, it can flip switch it. So maybe you'd end up with an engine firing before you intended that to happen. So, but what I found is that actually the biggest effect is the dust. There are particles out there we believe as big as I think it's 50 nanograms in mass, which is pretty big. And these things are microns across in size. But when they hit your spacecraft, which is moving at 20% speed of light, this potentially can have a devastating impact. It's like a little miniature bomb going off. But what you can do is you can look at the particle distributions, because there's an average mass of particle, dust particles, or mean, and there's the smallest and there's the largest. And what you find, of course, is that there's less of the largest and more of the smallest, and there's a mean between them. And so you can play a statistics game. And I think what you do is, it's not the fact that you just launch one of these things. You can launch many of them, because once the architecture is in place, you can just launch thousands of these in principle. And then the probability of you getting through is quite high. So you have to accept that a certain fraction of them will be lost because they will be hit by a large dust particle. But a certain fraction of them will get through. What that fraction is, I don't yet know, because it really depends on, our knowledge of the interstellar medium is pretty good, but there's still a lot we don't know about it. We've got an idea of what its matter density is, what the proportion of particles to dust is, and so forth. But this is one of the reasons why we need the 1000 AU mission and the post-Voyagers, because we could really, start to take some better measurements. One of my concerns about the Voyager probes, very successful, but I learned that, for example, the magnetic field measurements, the actual magnetometers on board were designed to measure magnetic fields around Jupiter, the gas giant Jupiter, and those magnetic fields are quite large. And so the sensitivity of the instruments were designed to measure large B fields. But of course, when we're talking about B fields in the interstellar medium, they're much smaller. And what I discovered is that the actual, what's called the standard distribution, if you like, the margin of error on those measurements is what's called 1 sigma, which is very low. In other words, we have the magnetic field measurements from the interstellar medium, but we have low confidence that those are giving us an accurate picture. And so we need to send another probe or more probes to actually characterize that data a lot better, so that when we come to launch in Starshot, we know exactly what we're flying through.
That's a really, really obvious thing that has to happen, isn't it? So in terms of, are there any numbers when it comes, because I'm thinking if you're launching thousands of these probes, are there numbers in terms of how much does it what's the biggest kind of factor about what that number is? How expensive is the actual launch of a probe in terms of switching on the laser beam and working it for 10 minutes? What's the cost of that compared to the cost of building this tiny little probe? Presumably it's the laser that's more expensive than the probe at this point.
The actual cost of the probe is tiny. It's the biggest cost by far is the laser. The problem, if you look at the moment, so we talked about Moore's law in electronics, and we know roughly where we need to be in 20 years' time with that technology to get more instrumentation on board the tiny little probes. So these things could, in principle, could be as small as a grain of sand with a 3-meter sail pushing them. So I forgot the question. What was the original question?
And in terms of the laser itself, presumably that is a very expensive cost in just running that laser, because the energy must be enormous.
The cost of laser is something like $100 per watt. Forgive me for using dollars, but
that's fine.
It's off order, so you can use pounds and dollars. So what we need to do to bring the cost of the flight down to about $10 billion is we need the cost of the laser to come down to about 5 cents per watt. So you can see that's an enormous reduction in cost, but that's over the next 20 years. And the guy that's really pioneered a lot of the studies on this and was one of the founders of Project Starshot is Phil Lubin from University College Santa Barbara, California, Santa Barbara. And he's done some extrapolation studies, and he believes that the cost of lasers will come down to that sort of level over the next 2 decades. And that then makes the mission viable. If we can't, then the total cost of the flight, in terms of building the architecture at least, just to get one flight, it then goes up. And so it's difficult to justify it. So you are dependent upon that. There's 3 kind of poles in the tent for Project Starshot. One is the miniaturization of electronics. The other is the laser, getting the cost down and being able to, no one's ever built a gigawatt power laser. That's the other thing. Got to build gigawatt power lasers. And thirdly, it's the array itself. Because remember, we're not just talking about one laser. we're talking about potentially hundreds of these lasers, all converging at a point. This is called a phase laser array. And it would work in a similar way to, say, fiber electronics, fiber communications technology. So to converge that light signal onto the spacecraft. One of the other issues you mentioned was the possibility of ablating the spacecraft, the SAL itself. Greg Matlock, who's one of the members of the advisory committee, has done a lot of good work on the possibility of using graphene technology. And there is, some belief that if you make a SAL, if you're talking about solar cells from the sun, they require high reflectivity. So all the light that's hitting it wants to basically be bounced back off. That way you get 2 times the push. That's the momentum that pushes the SAL forward. Well, with these graphene cells, potentially you can reflect a lot of that energy. So there's a lot of work being done in graphene cell technology. And that would allow you to absorb the high temperatures as well, which may be 1,000 Kelvin from these lasers, so that you don't completely irradiate it.
Yeah. So the other thing, of course, is you've got these tiny little interstellar probes now that are whizzing their way across interstellar space. But once they get to their targets, there's no slowing down, is there? They're just going to whiz past the targets, and you've got a very small window of opportunity to do science. So what are the problems around that particular part of this?
Yeah, you're right. It is a flyby mission only. We had the same problem in Project Icarus, building on Project Daedalus. Project Daedalus was also flyby only. It flew through Barnard Star in principle in 4 days, and this is a massive structure. We decided when we started Project Icarus, which is a fusion successor to Daedalus, that we would decelerate. We've demonstrated on paper we can decelerate into full orbital insertion. I think our argument is that in order to justify the cost of such a mission, you have to be able to put orbiting satellites in place, observers. You have to put atmospheric penetrators in and ground landers. Because then you can visit all of the planets in that system, and you can get so much science. You can look for evidence of microbes or whatever, look at the geology in much more detail, get through the cloud layers. A flyby probe is so limited, but Starshot, it'd be very difficult to try and decelerate these probes. There has been work done on looking at the deceleration. There was a paper, I think only a couple of years ago, talking about the possibility of decelerating them in the atmosphere of a planet, but I'm not sure that works. The fundamental problem is these things are moving at 60,000 kilometers per second. They have enormous amounts of energy. You just do the half mv squared calculation, you see these are like little bombs coming in. In terms of stars, for example, if you wanted to do gravity assist around a star, your spacecraft needs to be going at a comparable velocity to the star in order to benefit. So you probably want to be going something like 500 kilometers per second or less in order to get any benefit from a gravity assist. So gravity assist is ruled out. So really, these are flyby probes. But the current architecture was that we just want to take a photograph of an exoplanet close up. I mentioned the difference between Hubble and New Horizons in terms of what we got for Pluto. So that argument is certainly sound in terms of if you just take one photograph of an exoplanet, you should get a much better image, provided you can get the data back, than you would from long baselines, interferometers in Earth orbit. But there is a cost issue. But taxpayers are not funding this at the moment. This is a privately financed initiative funded by Silicon Valley billionaires mainly. And I guess they can choose to spend their money how they want to, and thank God they are. But I can see a point in the future where government might get involved in helping to fund some of these projects if they start to show a significant science benefit.
Yeah, I always struggle to think of, because you're right with the electronics side of things getting smaller and smaller and smaller, and I don't doubt that in 20 years' time we'll have electronics that are capable of doing some of the electrical side of things. But the things that I do find hard to wrap my head around is with things like, you say, just taking a photograph of a star as you whiz past, or a planetary system as you whiz past. It is the actual camera itself. It seems that kind of technology isn't really that shrinkable when it's all about resolution. There's very specific mathematical equations about the resolution that you can get with aperture and things like that. How does that work? What's the work done on that?
I'll have to pass on that because I'm not an optics person, camera person. I know that when I was in Initiative for Interstellar Studies, which I co-founded with Rob Swinney, we did a project called Andromeda project, which is actually how I got involved in Project Starshot. And we did that study for Project Starshot before they went live. And they basically said to me, I had a meeting with Pete Warden in San Francisco, and he said, okay, so we're launching this project. We're looking at launching this project. 10% of the speed of light is what he told me at the time. I didn't know later it was going to be 20%. Something that's gram scale in mass. Go away and see what you can design. So me and my team, in 3 days, we produced a report. And bearing in mind, I was flying from San Francisco back to, I got stranded in New York for a night, and then back to England. On the plane, I was calculating, pen and pencil and calculator out. And my team was all calculating. We had about 15 people involved in it. And by the Tuesday morning, we had a paper on their desk. And we managed to get the whole mass. I think it was 420 grams was our probe mass. Moving at 10% speed of light, pushed by a 1 gigawatt laser in Earth orbit. Okay. And what we did is we had a segmented lens array. So instead of having one collimating lens, we had 10 of them going out to Mars, about 2 AU. And that was to recollimate the beam. And that was using architecture created by Jeff Landis, who's a NASA Glenn scientist. And we demonstrated that was possible in principle. But what we did is we stuck quite a big camera on it. Our systems were kind of wafer size, like a stamp size. So 420 grams, but their initial response was, you're too mass heavy. We went away, stripped, because we had lots of instrumentation on it as well, because we were driven by the science. We stripped off a lot of the science. We managed to get the whole thing down to about 25 grams or so, or 28 grams. So I don't know. I mean, what cameras can do in the future, I don't know. You're right. I mean, because it's all about collecting photons, right, on the surface. So if you have a smaller aperture, presumably you're collecting less photons per surface area. So I don't know. I mean, maybe there's things you can do where you have several of these and they're kind of linking up together, and you're combining the images. I would say that's not got a lot of attention because it's considered a low priority, because it's really just a microelectronics issue, but an optical issue as well. And I'm not qualified to speak on the shrinking of telescopes to that size.
Yeah.
But our focus has been on the big poles in the tent, which is can we build a laser that big? Are we going to vaporize the cell? Can we survive the journey? And once we've ticked all those boxes and we think we can do those things in principle, then it's like, okay, what's the probe going to do when it gets there? Can we take the images? Can we get the signal back? And that's another issue.
I was going to say, that was the big one I was going to ask next is, in terms of, because you're now at an interstellar distance, getting a signal back, you'll need quite a lot of energy to do that. So with something gram sized, it's quite hard to perceive of where that energy comes from.
Yeah, so we've had a lot of interesting discussions about that, and because when I give talks on Project Starshot, it's invariably the question I get the most is, how are you going to get the information back? And I'm not a comms guy. I can just about do a link budget calculation. I'm a propulsion guy mainly. But the guys at Breakthrough are confident they can do it. I mean, we got David Messerschmitt involved, who's one of the world authorities on interstellar communications, and he's written several massive papers on it, and they believe they can do it. I mean, you're talking about the power of this signal is something like 20 watts, which is incredibly small power. But so maybe you've got to try and pick that up over light years distance. But what they are planning to do, you won't be using the Deep Space Network probably. What you would be using is the laser beam itself. So the laser beam, it basically doubles as a receiver. So you've got this huge ground space station of these lasers on Earth, maybe in a desert somewhere, and there's hundreds of them, and together they could also in principle pick up that signal collectively. So that's the current thinking, is that they would double as a receiver. There may be other ideas, like you could put a receiver on the quiet surface of the moon, maybe on the backside, and try and pick a signal up for where it's quiet. But or you could, if you had a probe out at 1,000 AU, maybe that could play a role in bootstrapping that signal to boost up to a larger amplitude. It's not something, the communications is not something that the guys have focused on with too much priority early on. As I say, the focus was on the SAO and the laser, because the SAO, which is another issue in terms of stability of the SAO. But I think that emphasis has now changed, and they now have formed a communications subcommittee discussing it. But from the initial discussions over the last 2 years, they seem confident that they can pick up that signal, which is amazing. I'm just not privy to all the details of the specs.
While you were sitting there, I was having the idea, based on something I was talking about on the podcast a couple of weeks ago, is as it's going so fast past the star, it will get to the point where it's at the gravitational focal point of that star, which of course you could then use to transmit the signal and have it amplified by the star itself back to where we are. But I guess,
and that's at about 1,000 AU, by the way.
Yeah, yeah. So that would be, I guess, one way of doing it. But I mean, I'm sitting here. My gut feeling is that if we want to do interstellar missions, that we need big craft to do it. That there's going to be, at the end of the day, I think that it's going to have to carry its own propulsion, be big, so that you've got this enormous power for doing things like sending signals back, or like doing inserting yourself in orbit, or going on to do other missions, etc., etc. Where does that then take us? Is that something that's being looked at, sort of the actual vehicle itself being having the propulsion on board and the technology and all the science, etc., on board?
Yes, it is. I mean, you're right. I mean, the projects like Starshot and other ventures we might launch are really exploration missions. They're certainly not colonization missions. They're just really taking the temperature of the water, if you like. They're telling us a little bit about what's out there, improving our knowledge of the interstellar medium or the properties, confirming that, we think there's an exoplanet and now we've got a picture of it. This all helps start build. It's reconnaissance, right? So ultimately, humankind has to build a starship and get out there. It probably wouldn't be like Enterprise, with a big warp drive, but it may be similar in that you would have literally crew members with families on board. I mean, let's assume that we don't achieve any life extension, as some people are working on at the moment, and we only live to sort of 80, 100 if we're lucky. Then the first crew that's on board, maybe they're in their 40s, 30s or 40s. There's an argument you might want to go younger. But certainly, to get to the stars in sort of even 100 years, as I say, you have to go incredibly fast, 2,500 AU per year. And but even when you get there, your crew has died. And so now you've got a new generation. So you have to have a generation of babies born on board. And then you have to train them to run the ship, to prepare the power systems, to, repair the communications, and to do the astronomy, and explain to them why we're out here, And what I find really interesting is that, it's when we look at history, all the great adventures of history, whether it's Columbus who discovered America, he didn't discover it, of course. So there was lots of people living in America when he got there. But all of the great, mentioned Kon-Tiki and Fort Heyerdahl, that sort of mission. All the great adventures of history. When you think about all the adventures we still have to have, whether it's in the past climbing Everest, in the future we're going to climb Olympus Mons on Mars. This is a great adventure that still awaits us, and without doubt, it probably will be full of tragedy. People will die because some missions won't be successful, and some will be successful. What I find interesting, actually, the idea of a world ship, which is what we're talking about, and again, Alan Bond and Tony Martin produced some of the first pioneering papers on this. They looked mainly at the propulsion and the habitat mass, how much atmosphere you need, and so forth. But what I find really interesting is whenever I get into discussions of world ships, it's not the technology that dominates the discussions, it's the social culture issues. It's like, what kind of a governance structure would you have that works? Because can we say with confidence that we've tested all of the governance structures on Earth at the moment, for all our different ideologies, that we know which one works? Because so far they've all got their downfalls, and we look at how we're handling the COVID-19 situation. It's doesn't necessarily reflect well on our governance models. So how would you manage a starship of maybe 1,000 people? How would you police it? What would happen if there was a pandemic that broke out on a starship, right? You're going to isolate everyone inside their tiny little crew cabins. How much support mass do you need? This is why the studies by Gerald O'Neill in 1970s are very important, because I think he concluded you need something like 65 tons per person of supporting mass in terms of water, food, oxygen, for a space habitat like an O'Neill colony. The Russians have done studies. They conclude, typical of the Russians, you could get away with a lot less, like 15 parts per kilogram. But it's something in that range that, maybe sort of 10 to 100 tons per kilogram for a human being. And so if you had 1,000 people, and that just running that numbers up, and you start to get a massive structure, never mind adding on the propulsion system, the power supply. So probably what you'd want to do is to have a strategy where you'd have either several starships or is one starship, but you cordon off. So there's different colonies, right? So, and those ideas have been explored in science fiction. This way, if there's any problem in one, the others can help, or you're isolated from the problem. If it was a pandemic, for example. And you need to have the ability to automate reusable materials on board. So if something breaks down, you need to be able to manufacture those materials on board. And this is the beauty of 3D printing, because it has massive implications for the future of space travel. Ultimately, I've looked at all these ideas for world ships, and they're very romantic, and I quite like them. One of the I think thoughts I've had is that this is probably not the way in the long term we're going to explore deep space. And there's a limit to how far you can go, which we can get to. I think it's more likely that maybe you'd send something like a Starshot probe, which would be easier and cheaper to do. And as it gets towards that stellar system, it grows itself, right? So it's like a biological, organic starship. So it's starting to get the light from the stars. It's approaching it. And so it's got energy. And that energy starts to grow the structure in the way that a plant would grow, or a crystal would grow. And it starts to construct its own starship. And maybe once you've built the fundamental structure, it then, the program would tell it to start to then take the embryos that you've got on board and to start to grow those. So maybe you start to grow a few crew members. And the robots, the artificial intelligence, which is what the probe will be constituted on, will do all of this. They will do all of this thinking. And then you get there and you arrive at your planet, or you arrive at your moon, or wherever you're going, or just your orbit, and you grow everything in situ. In principle, you can grow an entire civilization just from starting from that little premise. And I think that's probably likely the way deep space exploration is likely to go in terms of humans getting out there, unless we can find a loophole like wormholes or warp drive. And at the moment, the evidence is not strong that we could do that.
Yeah, I mean, it'd be a really strange. I mean, that's a great concept. I'm just trying to unpick all the very strange, odd things that can come out of the. If you send identical probes off to different systems and they've got identical crew members on board, and they can communicate to each other and go, God, you look just like me. Yeah, there's a reason for that. Yeah, that's a very, very interesting concept. Not one that I've read in science fiction at the moment, I don't think.
Another thought about that is that talks with governance models and so forth. If you were sending a whole crew of people, people can criticize certain ideologies on planet Earth, like certain religious belief systems. But actually, there is an argument that it may be that you need either a military or a strong religious kind of framework as the basis of that social culture in order to hold it together. Otherwise, you're just going to have people, having a revolution on board. The other thing I wanted to mention was I mentioned Arthur C. Clarke earlier. Arthur C. Clarke was a huge believer in the future, artificial intelligence will come. He actually described it as Homo electronicus. And he talked about this in Profiles of the Future, which I think was published in 1968. And he said that in the future, it's not that human beings will be driving the submarines and driving the spaceships. We will become them. Right? So we enter symbiosis with them. And eventually there'll be no distinction between us. So, we can actually experience what it's like to be an aeroplane or to be a submarine or to be a spacecraft. And so when we think about our artificial intelligence and gets to the nearest stars, that actually may be us. But then it goes to the question of what is us, right? So what does it mean to be human? Is it our physical makeup? Because in principle, as you know, all of the senses right now, I'm speaking to you, and I have all of my senses, my sight, my hearing, my touch, and it's all coming through, but that's transmitting information to my brain, and my brain is creating some imaginary reality based on those projections. But if I could put my brain in a jar, and I could also get those same stimuli through those senses, would I know the difference? Okay, so, and then we get to virtual reality, where virtual reality is going. So there's so much that's potentially in the future that it's really difficult to tell what direction it's going to go.
Absolutely. I mean, I always try and burst bubbles like this because these kind of thought experiments, like you say, they start to get out of hand in terms of there are so many layers to the onion as you get out and you go, oh, it's getting out of control. And I always think even the greats like Arthur C. Clarke, etc., didn't envisage the smartphone. And if we think how much that's kind of changed everything, that none of them got the smartphone. Star Trek, the smartphone in Star Trek, in the original Star Trek, would have seemed like the best invention in there, like better than the communicators, etc. So I always think it's just impossible to see how those kind of things go on. I mean, I love reading books about how those things play out, and that kind of humans becoming part of the operating system, becoming part of like a larger network. They're some of my favourite science fiction. I think Philip K. Dick does some of that stuff really, really well. And I've been mentioning to you, haven't I, about this guy called Rudy Rucker who does a lot of that stuff really, really well. It's somehow hilarious how he deals with it. But I think we jumped to world ships before we looked at the kind of intermediary bit between something like Starshot, which are these, like you said, they're almost like sounding rockets, aren't they, to these stellar systems. But in terms of robotics, large ships that have robotic probes going to interstellar, I think we've got that step before we get up to world ships and beyond. What is there in terms of, actually, yeah, let's frame this, go right back. Do you have a roadmap for how you see interstellar travel? So we're starting off with presumably you think we're going to be starting off with Starshot style probes. Where does it go on to next? And how do you see the roadmap of interstellar?
Yeah, I do. In fact, I just published an example roadmap in JBIS just in the last issue. Although I wrote that in 2011 for the 100th Starshot. I mean, whether Starshot ever gets to a launch remains to be seen, because there's lots of things that could, upset that program. But it's still doing fantastic research and so forth. You're right, there is an enormous gap between that and, say, world ships, big colony ships of people, which is, first of all, is the Voyager-like probes, which are much bigger in mass and but doing more science, and then you go up to the next level. We have looked at those in Project Icarus. I should mention Project Icarus is the what we did is I realized that I wanted to redesign Daedalus, and so we set about doing that. At some point, we ended up with over 100 people involved. We've now got about 5 Starship designs, all of which are solving some of the issues of the Daedalus project, because there's lots of reasons why Daedalus wouldn't work. I think I heard Alan Bond say it had a 40% reliability of actually getting to its destination, because there's lots of things that break down. There's little bombs going off 250 times a second. I mean, the heat and the fatigue on that structure is just so. So what you tend to do when you look at interstellar roadmaps is, first of all, there's the distance. Where what's the destinations we can go to? So I mentioned Kuiper Belt, the Oort cloud. There's getting to the nearest stars, and there's whatever else is in between, which we don't quite know yet. Maybe there's more dwarf planets like Sedna out there, and then it's how can we get there? What's the technology to get there? So the propulsion system is one of those elements. And so fusion obviously is not quite ready yet. We've got a inertial fusion program on Earth. That's my background, is inertial confinement fusion, and there's mostly the magnetic fusion is making inroads, I would say. But there's lots of other ideas for fusion. There's antimatter potentially, if we could figure out how to keep it stable and bring enough of the stuff together. But then there's these light beaming ideas, solar cells, which are really, in principle, dead easy, right? Because it's just a huge reflective sheet with a large area collecting photons from the sun, which is pushing it. The problem is, as you know, as gravity falls off inversely squared resistance, so does light. And so as you get further away from the sun, the pressure on the cell falls off. So in my opinion, solar cells are not really a good idea for interstellar missions, unless you furl an enormous cell, like tens of miles across, really close to the sun. Then you can get the acceleration. But whether the material could survive that enormous luminosity, 10 to the 24 watts, whatever it is, from the sun, 26 watts. So that's why you go to directed energy, because you can beam energy, or you could beam particles. So there's lots of these propulsion systems. What I would say is that there's very little going on in terms of other possibilities. There's lots of conjecture out there about space drives, which the idea of, there's the interstellar ramjet, the idea of mining interstellar hydrogen in the interstellar medium is sort of like a space drive, but it's not actually mining the properties of space itself, but it's mining hydrogen in space. But there's other ideas where actually we believe there may be energy trapped up in the quantum vacuum itself. And so if we could tap that, that would certainly enable a game changer. And there's very little research going on. There's been a few papers, there's been a few studies, and these programs just are not being funded with any kind of rigor and determination. So I would like to see some of that done. So if I was to sit down and someone said, okay, we're going to allocate several $1 trillion, which is what in the current environment, it's very unlikely because we just spent it trying to deal with the pandemic. It does amaze me how, by the way, when we had the financial crash years ago, we were suddenly able to produce billions of dollars to bail out the banks. And right now, I'm not saying we shouldn't, but we're producing, trillions to sort of help out with the economy and so forth before it crashes. And yet when we get back to normal times, even Apollo was like 4.6% of its GDP. The actual spending on space is incredibly low. And yet it's been estimated that, I saw a paper recently that the actual return on investment for Apollo was something like $200 billion on the economy. So you get enormous returns in space. In order to build a roadmap, I would say we need to do more research first. It's not to say that I don't want to do those one-shot missions. I'm a big fan of the moonshot idea. The idea of it's not necessarily a sustainable program, but you just want to launch something, and even if you just do it once, just to see what you can find out and what you can do. Okay, so and that's what I think is the value of Starshot, unless it builds that architecture up and it starts launching thousands of these things, and then that value is amplified even more. But I personally want to see a lot more R&D done. I want to see universities get more involved in interstellar flight, rather than it being seen as just a science fiction field, which I think historically it was. It's taken a long time to improve the credibility of the field. I mentioned warp drive. It wasn't until 1994 when a Cardiff University Mexican physicist, Miguel Cuvier, decided as part of his postdoc work to write a paper, because he can get away with it then, because it was just a Gedanken experiment, a thought experiment. And he wrote a paper on whether you could use GR, general relativity, to actually give you something like the warp into space. And that produced thousands of papers that followed. It started a whole field of warp drive, whether we could actually do it. And, in principle, we can. It's just there's lots of other things that, just like the thickness of the bubble has to be Planck scale in length. And it just creates such extreme energy densities that you effectively get like black hole singularity surrounding the vehicle. And it's just, there's loads of physics issues. So I would personally like to see more of the universities and even private industry get involved with some of these technologies. Maybe that needs to be done in a way that there's a contemporaneous benefit to human society. So for example, if you're developing more better power reactors than say the Voyager's got, or we can use at the moment, maybe those power reactors should also have potential to be used on Earth, right? So maybe there's an argument for that there's a parallel benefit to any technologies we develop. So that while you're developing the technologies for space, you're also developing the technologies to help Earth point one. And so there is a roadmap that you can go along, but I would say that at the moment we need to do more R&D, and I would say we need to spend at least a decade of rigorous R&D, of well-funded R&D with different institutions on all of the options. One of the bees in my bonnet is that if you look at all of the different studies for propulsion systems, for example, whether it's masers, lasers, fusion, antimatter, different types of fusion, cells, what you see is that there's no apples and apples comparisons. So when someone says, oh, this technology is better than that one, it's like, yes, but your payload was 1,000 times bigger and your mission time is this difference. And so what we need to do is we need to put things on a like-for-like comparison in order to see what the real potential is. And the best way to do that, I believe, is to throw those technologies, plug them into a mission platform. So like, let's say we decide we're going to do a 1,000 AU mission. So what's the different technologies that we can use and how do they compare, carrying the same payload, and do the same for an interstellar mission? And that's not really been done, in my view.
Yeah, that is really interesting. Yeah, I mean, that seems to make total sense. I mean, wrapped up in what you just said is something that I totally see, that I think's a point that the general public and maybe politicians don't get, and that is, whenever you invest in creative thought and in particular scientific research, you always get your money back. You always get that benefit back to society and then some. So, for example, I mean, the ultimate moonshot is obviously Apollo, and actually, thanks very much for that Arthur C. Clarke book recommendation, his scientific papers, because I've been reading those, and they're truly brilliant, because what I love about them is they put the historical context of the sort of 50s and what people were thinking like. And, they were thinking that space travel was completely ridiculous and how ridiculous it was, and we shouldn't be spending money on it. And even Arthur C. Clarke sort of points out how hard it's going to get to the moon, and we'll only do it a couple of times. He absolutely nails that, by the way, in that book. It's really, really good. But it's like, what I love about Apollo is it, and you absolutely said it in that, is that Apollo seemed almost pointless, really, of just like getting people on the moon. It's like, well, we've done it now, and then pack up and put all the time. But even that has managed to pay back into society way more than it cost society to do. And yeah, it is really frustrating when that message is very, very hard to get across, in terms of, yeah, we should be spending money on something like researching interstellar propulsion, because we will get that money back. We will get that money back because creativity is what generates the economy, as far as I can see. Or maybe I'm just being naive. But yeah, do you see it the same as that?
Yeah, I do. And in fact, I would say, I mean, I became a scientist because of Apollo. Without going into too much detail, I had an appalling time at school. I changed high schools halfway through. I spent most of the time fending other kids off, and it was I hated school. I wanted to learn, but I And what really put me on some sort of path was this Apollo exhibit, which really blew me away. I mean, I remember there were photographs of moon landings. There was newspaper clippings of President Kennedy's speech. There was a spacesuit, and I was living in a different world. I mean, I was in quite a lot of poverty at the time. My family, we didn't have a lot of money, and living on a council estate. And I saw this exhibit, and it was like a different world to me. And then I said, okay, so where do they do? Oh, Florida, right? So Florida, that's where. So then I became obsessed with Florida. So I would go down to the local travel agents, collecting magazines about, holiday magazines about Florida. And I would kind of became obsessed with it. I remember sewing myself a NASA mission patch, and I would walk around the house wearing it. All the neighbours thought it was very strange. And I here I am in 2020, and I say I visited every single NASA centre, and I've lectured at them. So my own trajectory started from very humble beginnings, and I didn't know at that early stage how I would get there, but I knew I wanted to work in space. I mean, I actually wanted to be an astronaut, like a lot of kids do. And that was really my ambition. I'm very envious of Tim Peake for his fantastic achievements. We're very, very proud of him. And I've met Helen Sharman as well. But I didn't know how I'd get there. And what became clear to me is that, okay, so you need to get an education. That's the first thing. You need to go to college, you need to go to university. And that's what really inspired me to get an education, not my schooling, which I found was dreadful. It was the space, the interesting space. And I hunkered down over several years, working hard, and eventually got to university, got my degrees and so forth. And so it also, I think it has the potential to produce a better human being, because I don't know what trajectory my life would have gone on if I'd have just drifted like a lot of young people do, not knowing what their place is in this world. And if I hadn't seen that exhibit. And so I thank the Potteries Museum in Hanley for that, who held that in 1989, I believe it was, because that would have been the 20th anniversary of Apollo. So there's that benefit as well. It's about making people understand that when you're caught up in your world problems, where's the next paycheck coming from, or what the risks are to you and your family in terms of survival. It's very difficult sometimes to just look up and take a broader perspective about life and the universe. And that personally has inspired me. It ripped me out of my reality and made me believe there was another reality. And so I wanted to go on a journey from the one I was in to the one I wanted to get to. And although I never, became an astronaut, I certainly got to meet a lot of astronauts and have a lot of fun along the way. And I was involved in founding a lot of space organizations, whether it's for-profit or non-profit. And it's been hard work, but it's been a journey. And I'd like to continue that journey because I don't feel like it's over. But space is, one of my friends, Martin Fogg, described it as space addiction. The problem with space is that you can really get into it too much, and it completely takes over your life. And so you also have to find a balance. You also have to remember there's other things to think about. There's the beautiful planet we're on, planet Earth, beautiful places to go. There's your children or whatever other hobbies you've got. But space is our future, and I wish that sometimes we could help the politicians understand that yes, our future on Earth is about making a better world, but it's also about where do we go from here as a civilization, and what's awaiting us to be discovered. You think of all of history. I mean, you can see this banner behind me, which is the logo for the Interstellar Research Center. That actually has a remit of looking at not just space. One of its questions is, can we get to the stars, and is there intelligent life in the cosmos? But I began to realize that to properly understand the place of a human being in the cosmos, you need to encompass pretty much most of the disciplines of human thought, whether it's history, geology, climate science, whether it's psychology. It's all very important in terms of helping us to understand. So this is a huge journey we're on. And so I got really interested in studying, historical interglacial periods, ancient cultures, quantum mechanics and general relativity, how you can unify them. understanding questions like dark energy and dark matter. And so that's really what the Interstellar Research Centre is focused on, is these big questions. What is time? So that we need to understand. And I although I would certainly advocate for interstellar missions. If another billionaire turned up tomorrow and offered me some funding to try and get a mission going, whether it's human or a robotic probe, I'll give it my best shot anyway. But my own maturity is telling me that as a species, we're not quite ready yet. We're very immature. There's too much fighting between us. But I'd still like to see us attempt it, because I think that the act of attempting something changes us. Just like going to the moon. The act of going to the moon was nothing about science, really. It was about politics, beating the Russians. But the act of doing it changed society for the better. And I think that Interstellar has the potential to do exactly the same. One of the missions I've often talked about we should be doing is catch up with the Voyagers and take a photograph of the Voyager probes. It would just be so much fun. Like, everyone's waiting for that photograph to come through. Here's Voyager 1 out in the deep depths of space. Here's an actual photograph of it. It'd just be amazing to see that. And I think that would be a really cool competition, like an X Prize. Build a spacecraft and catch up with the Voyagers and take a photograph of it.
Yeah. I think that's exactly right. And I think that really goes back to the very first point that you made about of having a vision for what humans can be and what we can do is saying this is where we want to get to, and that allows us to draw the map of how we're going to get to it. And I think that's what often is missing in society, where people just think, right, we just got to keep the economy going. That's all we should be really thinking about. It's like, no, we should be thinking beyond that, because we need to be able to get to somewhere, that there's a journey, that there's a destination, and how do we get to it? Or maybe there isn't. I know that some people philosophically argue against that destination thing, but I just think they're crackers. I tell you what, I think we should leave the Interstellar thing as the podcast. I'm going to ask a question that I'm just going to put on our Patreon channel for our patrons. Thanks very much for the Interstellar stuff. So here we go. I'm going to ask you about your current thing about conscious stars. What that's about?
Yeah. So I began. First of all, I started thinking about SETI, Search for Extraterrestrial Intelligence, and I visited the Chelsea Hotel in New York, and I was trying to get into the exact room where Arthur C. Clarke and Stanley Kubrick had their big debate about what the aliens in 2001: Space Odyssey should look like, because that's where Arthur was writing the book and the movie transcript at the same time. And Arthur, I was arguing they wouldn't look anything like humans, and Stanley Kubrick wanted them to be humanoid, and they couldn't decide. And it turned out Carl Sagan was in town, so they called him up. So he went to the room as well. So you can imagine that hotel room. Stanley Kubrick.
As cool as it gets.
Carl Sagan. And it was Carl Sagan that suggested, my understanding is he suggested, don't show the aliens. Leave it up to the imagination of the viewer, which is why you don't see them in 2001. But that's an interesting debate. What would life look like? And then in other star systems. And then it's a question of what is life, right? So Erwin Schrödinger, the physicist, wrote a book, What is Life? I forget when it was published. He also one of the people that predicted the DNA molecule, essentially. I think he called it the organelle. But he argued that we should take a different perspective, more physics definition of life, such as life is resisting the decay to thermodynamic equilibrium. Okay, so this got me thinking about life first of all. What would life look like in other systems? Would it be humanoid, or would it be radically different, like huge globulous jelly-type fish in a gas giant, for example? And then what's intelligence, right? So this is so I became interested in the orchestrated objective reality theory of Stuart Hameroff and Roger Penrose, which I think is a very elegant theory. The idea that consciousness is not defined at the neuron level, but actually at the microtubule level. So instead of having something like, artificial intelligence advocates believe that consciousness is defined by something like 10 to the power of 16 processing operations per second per brain. If you take the Hameroff model, which includes the extra 10 billion or so processing operations in the microtubules, then you're up at something like 10 to 26, 10 to 27 processing operations per second per brain. And so that got me thinking about consciousness. Now, it turned out that a friend of mine, Greg Matloff from New York City College of Technology, had come up with an interesting idea a few years back. He was looking at dark matter, and he was not convinced by the current explanations for dark matter and galaxies. You probably recall that the basic problem is that if you look at the motion of stars in the galaxy, they should have by the Kepler's laws. So if you imagine a plot of velocity against distance, you should see the velocity sort of going up and up, but it flattens off unexpectedly, implying possibly that there's more mass in the galaxy than we see, hence dark matter. Maybe it's matter we can't see, it's non-luminous. And there's all kinds of explanations being proposed for dark matter. But Greg was looking at, in particular, stars in the outer parts of spiral galaxies. He was making the observation that, if I remember rightly, that red giant stars move at very different velocities to blue stars. And this is something called Parenago's discontinuity, and no one quite understands what it is. But Greg, I was running a symposium quite a few years ago now, the BIS, on Olive Stapledon, who was a British philosopher from Liverpool who wrote a couple of wonderful books, Last and First Men and Star Maker in the 1930s, who also influenced Arthur C. Clarke. And Stapledon had the idea in one of these books, I think it was Star Maker, that stars were actually conscious entities that were moving under their own volition. And I don't want to spoil it too much, but there's a horrendous scene in one of the chapters where the stars start committing suicide. The stars start going out. I haven't read it for some years, but it's an amazing book. And and this ultimately, when Freeman Dyson came up with this concept of Dyson spheres, which really should be called Stapledon Dyson spheres, the idea of trapping an enormous radiation cavity around a star to, like a high Kardashev civilization would do, to trap all of its radiation. He was actually getting the idea from Stapledon. It's just that he wrote this paper in the 1960s. Actually, I only read it the other day. It's literally one-page letter published in the journal where he does these amazing calculations. But then I had a thought that, I should go back, that Greg, we organised a symposium in London, and Greg couldn't make the symposium. So I presented his paper for him, which is on Olive Stapledon's idea of volitional conscious stars, which is a very controversial idea. And at the time, I was editor of Jabers as well. And we managed to agree to publish a letter on it in the journal. And that got him started. And since then, he's been writing lots of papers, a book, and giving lots of talks on the idea that stars may be conscious entities. Now, this is really interesting because, of course, lots of the historical religions in the past have worshipped the sun like it's a god. So I started these conversations with Greg and a few others, including Rupert Sheldrake and Julian Goff, Philip Goff, and Clement Vidal. And we've been discussing conscious stars, and this for the last few months. And we were meant to have a meeting in June, but we rescheduled it. It's a private meeting, but we're having these really interesting discussions on the idea of whether a star could be conscious. So, I've not made up my mind, because I studied astrophysics on my master's degree, and I did stellar structure and evolution, and I understand how stars are created and how the gas cloud fragments and collapses and produces fusion ignition when it gets to a certain percentage. I think it's 8% of the mass of the sun, and then you get stardom and fusion ignition of the core, burns the hydrogen for billions of years, and it moves through the main sequence eventually. Eventually blows up to a red giant. Or for other stars, they become supernova. And some stars become black holes if they're massive enough, more than about 3 times the mass of the sun. So I have studied astrophysics and stellar structure, and I think we have a good handle on the equations of a star. So I was a bit skeptical. But I started doing some calculations just out of interest, as a thought experiment. So on the idea of volitional motion. So Julian had suggested to me that could a star actually use its stellar wind or coronal mass ejections to push itself? And so I've actually been doing those calculations in the last week. And originally, when I did the calculations, I concluded it's just too weak. I mean, it's like 1 million times weaker than an ion thruster. in terms of the actual, if you assume it's like a big rocket, it can push itself. But I've since rerun those calculations, and with coronal mass ejections in particular, and it's amazing that you can actually get up to decent velocities and actually push the star. And I found that actually, it's possible to move the star over tens of AU in something like 100,000 years, which is actually comparable to the time scales for collision avoidance of another stellar system. If there was another planetary system coming towards us and it looked like we were on a collision course, when I say collisions, I don't mean the stars are physically going to touch all the planets. They're too far apart, but I mean that gravitationally they will get so close that they will perturb the planetary orbits. And I found that the actual adjustments you need to make to the star's position to move it away from that risk is that similar sort of timescale. It takes of order of 100,000 years or so. So it doesn't mean to say that I think stars are conscious. I'm doing it as a thought experiment, and I wrote a paper on it, which just gone out to those guys, and looking forward to getting their feedback.
Yeah, it's when you said it to me, it really just reminded me of one of my favourite ever bits in any book ever, and it's Rudy Rucker's Ware Tetralogy. It starts off with I think it's hardware, wetware, and it just goes and it's all the different wares. I can't remember what order they're in, but I think it's the third book. Consciousness has been able to be transferred onto this mold. It's kind of weird mold type stuff that has a kind of mold. It's kind of like that, but it's a totally weird thing that's in the book that sort of comes into. He mentions it in a few other books as well, but this mold takes on a personality, gets loaded with a consciousness, and one of the main, there's two main characters that are molds, and they're traveling in a spacecraft when they're bombarded by a stellar wind, and that stellar wind has all the information of a stellar consciousness embedded in it, and the stellar consciousness is able to use the mold to come alive. So you lose two of the main characters that you've just come to know in one page, and it is taken over by a stellar consciousness.
Yeah.
And Rudy Rucker's very much about the consciousness being in absolutely any object that has enough complexity to be conscious. But it's a really, really interesting concept in that book, and it's dealt with all the way through, and it ties back to the very early books where the AIs and the robots have stellar wind as a way of randomizing their thoughts, and then it turns out that they've been directed by the stellar consciousness all along. So it's a really it's a great sci-fi concept, but yeah. I mean, it would that really would be the most astounding explanation for dark matter ever, wouldn't it?
Yeah, I mean, I have to say that I'm not optimistic that this is what dark matter is. No. I have my own ideas for that. I won't go into at the moment, but I would say that I think it's an interesting. It's not even at the level of a hypothesis. Right, so in order for a hypothesis to, you have to come up with a testable prediction. Greg Matloff would argue with me that it is, because he's come up with a way of testing it, but and it's related to ideas of panpsychism. But I think in order to get to theory, then you need to develop the evidence. So I would say it's conjecture at the moment, and but I'm a physicist and I like doing fun things, so I just thought I'd run the calculations on the volitional motion idea. And I'm still sort of, as I say, in the steps of doing that. I'm also looking at the idea of a star as a brain, comparing it to, this itself is questionable, human consciousness. So we know that the neuron compaction density in the brain is pretty high compared to other mammals and other animals on Earth. So if you just take human consciousness, I mentioned the sort of processing operations speed earlier, sort of processing at 100 hertz. And then you can look at the similar sort of what's the processing speeds in a sun, in the star, in terms of how fast are sound waves moving, What's the the helioseismology? What's the frequencies of those? And just a very quick cursory look. This is not published work at all, and it's literally back of the envelope stuff. But I've concluded that if a star was conscious, then it's thinking a lot slower than a human brain, possibly of order 10 to the power 5 times slower. Which is interesting. That 10 to the 5 number is also, the 100,000 years I was talking about. And that makes sense in some ways. I mean, when you think about, there's ideas of trees or forests that have some ability to communicate with each other. If a forest, there's a certain tree which, if it gets infected by a particular aphid, and it starts generating a fluid, a pus. And the purpose of that is to alert all of the other trees in the forest. And all the other trees then develop this pus. And it's to basically ward off the aphids, right? So there's an argument that trees have a form of communication, but we don't recognize it because we think in very quick timescales. We think in terms of human timescales and the rest of the animals in our kingdom. But actually, if there is a consciousness in other systems or consciousness-like behavior for big systems like mycelium or forests, or stars, I think it would be a lot slower in terms of the thought processes. And so that makes sense that a star would be thinking a lot slower. But then that brings a problem for me in terms of if it is the case that it's thinking of order 10 to the power 5 years, 10 to the power 5 times slower than the human brain, then, how is it getting the information about, volitional motion? How's it getting the information that there's a stellar system coming towards it? Because it takes a long time for that information to arrive, but it actually relative to that speed, it's quick because it's traveling at the speed of light, right? So it knows within years, but then it's got to process that information in its huge brain. So it's an interesting idea. I would say it's in the phase of science fiction. Another thought experiment I came up with, or an observation I should say, which I pointed out to my colleagues, and I think they hadn't realized this themselves, is that if it was the case that a star was conscious, this actually then prohibits Dyson spheres, because it would not be moral or ethical to put a huge radiation cavity around an entity that we think may have some level of consciousness. And so if we can prove that stars are conscious, which I'm not optimistic about, this would, in my view, make it less likely that you could ever build a Dyson Stapleton sphere. And the opposite is likely also true, because although morality and ethics will differ with different civilizations in the universe if they exist, I tend to think philosophically that they would asymptote towards a certain understanding of the respect of life and its value, and they therefore wouldn't do that. So it brings in the whole question of carnage of civilizations, the idea that carnage of one, you utilize the energy of the entire planet, carnage of two, entire star. Is that what you would actually do? Would you actually trap a radiation cavity around a star and capture all of its radiation? Because then you then prevent it from any volition of its own. It's effectively a star prison.
Yeah.
And to me, this is a humanism versus naturalism argument.
Yeah, I mean, you could argue that there's a similar sort of thing already going on with, say, Mars exploration, where if say Mars 2020 rover detects microbes on the Martian planet that are native to Mars, then some people would argue that literally puts the kibosh on us going to Mars to inhabit it, because we would destroy that. Well, we would go into a pristine environment and destroy that native life, and that wouldn't be ethical. So it's a similar sort of argument, isn't it? That exploration always has some huge moral choices, and it's the same with getting energy, etc., etc. There's always some moral choices somewhere down the line to have to make.
Yeah, I think my own perspective is that although I have enormous respect for the natural world, and I believe we should live in cooperation with it, not in competition with it, I also think that it is our first priority, think of it as triage, if you like, is human life as primacy. Is that our job is to first of all look after ourselves, and then to look after others if we can. So my argument would be that if we found microbes on Mars, and hopefully they were ubiquitous, and it wouldn't therefore matter if we farmed a few of them, or I personally would not allow that to stop our progress on Mars. I think we should build a Mars colony, and we should find a way to use those microbes for our benefit, to create an interesting ecology which we can exist in.
Yeah, I mean, I agree. I mean, I don't separate humans out of nature anyway. So I kind of think that everything we do is a natural process. I mean, I even call buildings natural because that's the way I see it. I think, we're just, every other animal behaves in the same way. Birds build nests, and the bird doesn't look at itself and say, God, I was building that nest over some moss. How unethical of myself. Mm-hmm. So yeah, I don't know. It opens up some interesting things, but it's a really interesting thing, stellar consciousness, and the thought that, I mean, that really would be such an incredible explanation for dark matter. I mean, we had one on the show a few weeks ago, which was dark matter is information. And someone from Southampton University was suggesting that in the same way that energy has mass, then maybe information itself has mass as well. And with a few calculations, she was showing that actually that would explain dark matter. If the information that's in a galaxy cluster or in a galaxy would be enough, this extra mass from the information contained within it would be dark matter.
Yeah,
it was really interesting.
Yeah, I have my own view on it. I'll maybe talk about it in a future podcast, but
yeah,
I'm doing some calculations at the moment. It's not something I've traditionally been interested in. I'm more interested in dark energy than dark matter, but I had an idea recently which I'm trying to pursue at the moment, and but I'd like to sort of get something written up and scrutinized. What I tend to do when I write a paper is I pass it around a few friends to act as my filters before I show it to anyone else.
Yeah.
But yeah, it's an interesting question. I mean, this is the other thing. If we go back to the space travel interstellar question, I mean, there's so much we don't understand. I mean, we've made so much progress in the scientific endeavor, particularly since the Enlightenment, but there's so much we don't understand. And, what is dark matter? What is dark energy? How can we test string theory? We still haven't discovered the graviton particle. We've only barely just detected the Higgs boson in the last couple of years. And so, are there extra dimensions? Is there any evidence of intelligent life outside of this biosphere, let alone life outside of this biosphere? What are we doing? I mean, we're just, these big questions are so obvious, and we should be really exploring them with vigor. And we're not. And the reason we're not is because we're caught up in our own problems and our own troubles. Too much nation-state rivalry, for example, and not enough cooperation. And we talked about the Chinese earlier. I actually learned when I was in Bremen that they're planning to launch a 100 AU mission, like a Voyager probe mission. So good on them. I hope that they do that, and it'd be interesting to see the results. I'd like to see maybe we can help them and make sure that mission is a success if we can get access to the data, because it benefits all of us. We definitely need a better cosmic perspective, and this is my own view of my own journey, which really started in about 2007. In terms of this kind of these exotic subjects, and is I realized that, first of all, I realized that I don't understand human beings at all, which is an interesting thing to realize. And my friends often tell me that I don't understand people. But secondly, we're so complicated. I mean, human beings, we're full of emotions, and we're just so complicated, and we're so disorganized. I mean, if we could just, something like Apollo, it forces us to focus on something, right? So, or something like trying to put together the Human Genome Project, or just these big projects really focus us. And I'm hopeful that one thing that will come out of this horrific pandemic which is, sadly seeing the loss of enormous amounts of life around the world, is that it refocuses our priorities a little bit, makes us pay a bit more attention to the broader picture, and also helps us to focus on what some of the existential threats really are to humankind. I mean, other than pandemics, like a lot of people, didn't know a lot about pandemics, but when this started, I started doing research on it and reading it, and it's like, oh, I didn't know about all those ones. And you see how many people have been lost over the years, and it's like we have this forgetful memory. We forget, but it's all in the books and in the history books. One of the periods in history I became interested in was the Younger Dryas, sort of 12,500 years ago. And there is pretty strong evidence of a cometary or asteroid impact on the North American ice sheet, which basically led to those massive melt flows of water, and ended the last ice age effectively. We know that impact events occur. We saw one, was it 2001? We saw the Jupiter collision, 2000.
Yeah. Well, whenever it was, that
was, and we had
Shoemaker,
Shoemaker leaving 9, and then we had an impact in Russia. It was only a year or so ago, and we know that impacts occur all the time. I'm not convinced that we're doing enough, because we can have a massive catastrophic failure of a society overnight. One of those impacts a city. If that one that hit Russia last year had a slightly different angle or different speed, come in at a slightly different entry point, it could have been a very different. We could have been talking about that. We could have been saying, how comes we've lost 500,000 people? We need to pay more attention to these bigger problems. Humankind is on this beautiful planet, the power blue dot, as Carl Sagan used to call it. And we're very fortunate. We've got these the beautiful jungles and the dry deserts, and the Antarctic and the Arctic, and just such very different terrains we can explore and learn about life, and millions of different species of life. But we really need to pay attention to the threats that humankind and all of the life on this planet faces in the bigger picture, whether it's pandemics or asteroidal impacts. And I would like to see more focus on that.
Yeah, I mean, it's so hard. I mean, you're saying that you didn't understand humans. I don't think humans understand themselves, or anyone really. It's very, very difficult to, particularly long-term thinking, long-scale disasters and catastrophes like pandemics. I mean, you'll have scientists that knew that this pandemic was definitely going to happen. It's like, this is definitely going to happen. But to be able to sort of motivate people and to be able to see that it's going to happen, even if they see a documentary and they're watching it and go, God, yeah, that's amazing. Next day, they'll have forgotten it. They'll have forgotten just how ridiculous we should be doing something about it. And it's the same with asteroid strikes. I mean, asteroid strikes is the classic one, and super volcanoes and mega tsunamis and all these sort of things. I mean, everyone's forgotten the nuclear threat as well, which is still very, very real. And it's like, yeah, how do humans overcome that psychology? And I hope you're right about the pandemic issue, that once the pandemic has been controlled and we're at the other side, that internationally we'll have a whole new mindset of thinking about these things. I just hope that the right people win the narrative at that point, because there's been certain times in history where horrible things happen and the wrong people win the narrative, and it's just like, they're missed opportunities in that sense.
Yeah, I think my perspective is that we need to get away from politicizing science. Whatever the field, I won't go into any specific fields, but whatever the field, science needs to maintain its objectivity and its ability to be non-biased. Science has as much color and flavor as any discipline of human thought. I mean, the humans, you only got to look at Albert Einstein's life to see how amazing his life was, let alone his physics. But we need to get away from the bias that influences science. Scientists should be in a position where they can, just like a professor who has tenure, in principle, can make a statement on a position of something, and there is little repercussions, because what's primary is the integrity of free speech. And when we lose free speech, we lose, I think, a lot, because yes, a lot of free speech can be inflammatory, or bigoted, or whatever pseudonym you want to apply to it. But I think that that's a small minority. What's important is diversity of views. So if there's any field of thought, whether it's what we should do about asteroids, pandemics, or climate change, or whatever it is we're talking about, I feel that science should be opened up to the maximum possible broadest views, and the integrity of those scientists' objectivity should be preserved. And then the politicians need to be better educated in how to take that information and turn it into policy, because I fear, in particular with the current pandemic, I'm not criticising. I'm in the UK, but I'm not going to criticise the UK government, because it's in a very difficult circumstance having to deal with this tsunami which rushed at us. Although you could argue it was predicted by someone, and we should have had better preparedness. But I do worry about they're listening to certain science advice, and to the exclusion of others. And Freeman Dyson took a view in his life that he was a contrarian. If he was in a room and there was a consensus developing around a particular viewpoint, he would deliberately take an extreme view that's the opposite of all the others, not to be awkward, but because it forces a debate. It forces a discussion about the subject. And in order to have a proper debate about something, you need extremes of positions. And that's one of the things I like about multiple religions around the world, because no one really knows the answers to, the omniscience and omnipotence of the cosmos. But they all have different perspectives, and it enables you to kind of take your own bearing and help to guide your own life, because you can look at those different extreme points of view. So this is where science needs to get back to. It needs to get away from politicization of facts and truth.
Yeah, it's amazing, isn't it? The philosophy of science has become not such a well-taught subject anymore. I mean, if you think back to the sort of greats like Bertrand Russell and people like that, Bertrand Russell pretty much says exactly what you just said then. He's very much about that whole, it's about the objectivity, but sometimes other people have different points of view, and you need to listen to them, and sometimes you might come to different conclusions, and that's that, and you just have to learn to live with each other and not want to have the truth because it's convenient, and it's just whatever the truth actually turns out to be, and you just have to accept it. And it's just like the philosophy of science is it's somehow not that trendy a subject anymore. It's not thought of as a kind of highbrow sort of thing. But I think you're right. I think it's actually extremely, extremely important, because the philosophy of science will tell politicians how they're supposed to respond to the scientists and everything else. So, I mean, the only good thing about this, the government response, I would say, to COVID-19 is at least they are listening to the scientists. At least there is science involved. Whether their particular response to it is perfect or not is definitely going to be something that's going to be picked at for years and years and years to come. But you can look at some of the other nations around the world and their failure to even engage with the scientists on the subject, and it's absolutely shocking.
Yeah, and also I think it's okay to disagree with people, right? There's the other thing: if people have a different, the actual definition of an argument is, two different ideas that sort of are not consistent, and it's okay to have. Doesn't mean it has to be volatile or aggravational. You can disagree with someone, but what needs to be the arbiter, the test, is truth. And so, if someone makes a statement about something, you should be able to test that statement against facts, against truth, what we know. And that seems to be where we are at the moment, is in a war for what is truth, which is a bit sad. And I think that war is happening particularly in social media, because we live in a poorly educated populace. If you go back to the Roman and Greek times, they talk about things like the trivium and the quadrivium, and the importance of mathematics and reasoning and ability to form a logical argument, and having knowledge of geometry and architecture and astronomy and all of the disciplines of thought. I think that the problem is people don't know how to construct an argument, and they don't know how, which means they don't necessarily know how to take apart an argument. So when you get people making statements of what they think is truth, or on science, which then has a bearing on policy, people don't necessarily know how to take that apart and understand whether the argument they've made is a valid one, or is it a logical fallacy, for example. And I frequently watch the news and just see politicians doing this all the time, that they contradict themselves in their statements. We saw that only a week ago, but I won't go into it. And so I go back to education. I think it's really important that we educate the people, the population. I mentioned that I came from humble beginnings, and my education really came about post-school, not during school. And I self-taught myself a lot of things. I read books on logic and reasoning and how to construct arguments and so forth. And this is really important because that's how you can see through the noise, particularly when we live in this world where we're just inundated with information. It's just so much coming at us every day through our iPhones, through the news, through the radio and podcasts, and what do we believe that's true? And I think that critical thinking is a really important skill, and it goes to all of our endeavours.
Oh yeah, I couldn't agree. That's one of the things that keeps me in my job as a lecturer. I think that higher education is so important, and for me, it's the kind of what I do notice is that the way that the school system has gone is that it's so results focused that, of course, as a teacher, you're sitting there going, well, I've got to get some good results, and there's a shortcut to getting good results, and that's to teach children the answers. And one of the things that you miss out on then is to teach children how to get to those answers themselves, teach them how to think, and teach them how to acquire knowledge, and teach them how to research. But if you've got this pressure of league tables and stuff like that, then of course it's going to go out the window. You've literally set up a system that skews the whole table towards the wrong type of learning. Yeah, and it's really depressing.
So one of my heroes was Richard Feynman, as a physicist, and he had the view that it's about understanding. So in principle, if you understand the foundations of physics, you can derive everything else that is claimed to exist, if you understand the foundations. And so that is, I think, where the emphasis needs to be, into understanding. So what I fear is happening is that children are being taught to pass exam papers, and they're getting lots of really high grades, but it doesn't mean they have an understanding. So they might have done some papers on equations of motion or something like that, but did he actually understand what they're doing? I remember even on my master's degree, I did an exam. My general relativity exam was a Russian teacher. Typical Russians are very, very smart people, and he announced at the start of the exam, no calculator. Right, this is 2002, and we sort of took a big breath of air. What, no calculator? We were horrified. It's like, how going to do an exam on general relativity with no calculator? And I basically had to do this exam paper, and I remember, doing these calculations, back of envelope, powers of 10 notation, and working out the coefficients. There's a particular problem I had to calculate with two neutron stars colliding, and I had to work out the wavelength for the gravitational wave. And I just remembered from memory that it was of order 10 to the minus 11 meters. And it was one of the proudest moments of my life when I got to this long calculation without a calculator, and I got to 10 to the minus 11 meters. I knew it was correct. But it turned out he was wrong to have done that, by the way. The university told him off for it. But my point is that, the ability to do those sort of calculations and understand what you're actually calculating is an important part of science. And it's the same in any field, whether it's languages or history. I think academic rigor is really important, but I don't think the best way to drive that academic rigor is necessarily through tests. Right? So maybe at the higher level, the higher age level, you need those exams. But I'm not keen, for example, on children being tested at all before the age of 10. I think children should be children, and they should just have fun and learn through fun. And I think that's what it should be about. I'm a fan of I can't remember his name now. It's one of the biggest TED lectures on TED. Sir, I can't remember his name. He's a former member of the Shakespeare Company in Stratford-upon-Avon. But he gave a very good talk on creativity, and I think creativity is also very important. He was criticising that the science, engineering, and maths tends to be given more priority. I'm not sure that's true, but he was trying to make the point that we mustn't forget about creativity, because creativity is what solves problems. And I also agree. I think creativity and imagination is very important. I mean, my daughter's very creative. My oldest daughter, she's just making things all the time. And I was like, how did you come up with that? And I try to encourage it, but she doesn't really need the encouragement. She's just making things, just astounding things. And we lose that as we get older. And
I don't even get the argument about maths, for example, not being creative. I distinctly remember, and I still have this, where writing a song or finishing a maths equation have exactly the same feeling of a creative leap for me. It's like literally, it's so creative to solve a mathematical problem in the same way of writing a song. It's exactly the same thing. So to be encouraged to be creative. I mean, creativity is all that we have. Particularly moving into the era of AI and machine learning and everything else, human creativity is going to become more and more and more and more important. Who cares that you can operate a calculator, because my computer can do it 5 times faster than you.
Well, it's the same with the conscious stars debate. I mean, it's probably not the case that stars are conscious. That's my position at the moment, but it's a heck of a lot of fun to think about.
I know, exactly, and that's why I love having that stuff on my podcast, because I think there is why not deal with something that would be considered outside of mainstream science? Well, just because it's outside of mainstream science doesn't mean that it's necessarily wrong. It just means that it's fun, it's creative, it's got some kind of it's not it's not just something made up that's completely ridiculous. It has some kind of fun element to it, and maybe it will lead to something. I mean, it would be the most astounding discovery ever. The dark matter was that, but yeah, I think that there's one point that you did make, and that's the this ability to sort of argue with someone and realize that you're arguing against the things that they believe and not the things that they think they are. And a lot of the time now, I think a lot of people are their entire narrative about who they are is wrapped up in their beliefs and the things that they believe in. And therefore it's very, very hard to have arguments, because the moment you start unpicking some of the things that they're saying, they feel as though you're having a go at them. And that is so common. And I must admit, I've never really had that. Occasionally someone will say something where it'll make me angry, but I realize how wrong that is. But I realize that when you talk to people, it's very, very hard to bring people out of certain positions that you feel are wrong, or that they're talking nonsense. And you only have to see how that how that kind of unwraps on social media. You say something, and if someone disagrees with you, they don't have a go at the point that you're making. They have a go at you. Yeah. They say, "Oh, you're an absolute 4-letter word for believing that." It's like, please just don't do the ad hominem thing. Just
it's an ad hominem argument in logic, but
yeah, I mean, that whole logical fallacies are a great place to start. I think when it's sort of looking at reason and critical thinking. I think that's
I mean, you don't want to go either extreme, because the thing is, if you just become a Vulcan, you just did logic. then
Yeah.
you kind of potentially kill the creativity, because you're only prepared to speculate based on tiny perturbations of the known, right? And so, but if you're prepared to be creative, I mean, the idea of thinking about a conscious star is not logical, because there's nothing in our knowledge of science in the world, the natural world, that you could extrapolate and say, therefore, it's possible a star may be conscious. It's very difficult. There's nothing you can extrapolate from. So therefore, it's a complete creative jump that's not based on any inference of anything that's known. But what you can do is you can apply our knowledge of physics, for example, and to that system, and say, well, if it was conscious, what would it look like? And then once you run the numbers, you can see what's possible and what isn't, right? So maybe there's a reality, another universe where such a thing would have been possible. This is the same for things like wormholes and warp drive. There's no evidence at the moment in physics that wormholes or warp drive exist, artificially or naturally. I would argue that wormholes are slightly more plausible than warp drive for different reasons. But however, people publish papers on them all the time. The idea of taking the Einstein field equation and taking the space-time metric and reshaping it to give a different geometry, a different coordinate frame, which then changes your equations of motion, and then you run the Einstein field equation to work out the properties of that system. And what you find is you need enormous amounts of negative energy in particular, which doesn't exist naturally in the universe. But we have ideas to create negative energy, something called the Casimir effect. So that's interesting. It's like, okay, so is it possible that we could create microscopic wormholes? Well, it may be. There are various reasons in physics for thinking it might be possible at the microscopic level. If you could do, because, they go down to the microscopic level, what is fundamentally space? You got the two competing theories of string theory, which sees tiny particles as like oscillations on strings. And that's really a kind of ground unified theory, successor to Einstein's pursuit of that. So it's a success to Einstein. And you've got others like loop quantum gravity, which is, they're actually looking at the discretization of space itself in a way that you'd have, say, atomic energy levels in an atom. Well, John Wheeler published a paper years ago where he showed that you go down to the quantum level, right down to the Planck scale, because of the quantum uncertainty, you have what's called space-time foam. And so space and time are intermixing, and you get all these little tiny chaos of, it's not, necessarily a continuum. It's there's just this chaos and of these dimensions coming in and out of existence. And it's possible that you can, in principle, take one of those dimensions and inflate it for a second, so it goes bigger. And then maybe you could pass a particle through it, or even a photon of information. Even just one bit of information. That's then, a form of telecommunication, which would exceed the light barrier. So that's one way we think we could do it. But this is, and this goes to spooky action of the distance and quantum entanglement as well, which is another subject. So we know there's some interesting things in physics we need to look at, which is pointing that the world is a lot more complicated than we think it is. The world's a stage, as Shakespeare said, but there's a lot of complicated stuff going on underneath it. And I'd like to pull back that curtain and see what it is.
Yeah, we all would. Well, if only I was brainy enough to even start. It's really fascinating. All that stuff of where can we go? It's amazing, isn't it, that like 30 years ago they thought they'd almost solved science, that we were almost there, that we were at the
even Hawking said it.
Yeah. And it's just like we seem further away now than we've ever done, because we've opened up so many different areas of things to look at. Now, the point I was going to make about your stellar consciousness, I think what's great about that is the having that creative urge to have a look at something like that. And you never actually know that the stellar consciousness might be a complete dead end and complete waste. But it'll never be a waste of time, because you'll be able to see. It may have given you insights into something else. The fact that you've done these equations to look at what other things might be conscious, you might someday be walking down the road and have another insight that you wouldn't have had you not have sort of put your brain to this other puzzle. And that's what I love about creativity. It's this never-ending onion that keeps going down and down and down and down and down. And the more creative you are, suddenly the more ideas keep coming in. This is what, I mean, songwriting, for example, is classic. The more songs you write, the more likelihood it is that you're going to hit across this great, great song.
Yeah.
And just because you wasted your time on a song that was fairly mediocre or even rubbish, that song, you may not have been able to get to your great song without writing this mediocre song. So don't worry about it. Just enjoy the process.
Yeah, I agree. It reminds me of, you go off into the Amazon rainforest because you've been given a grant to try and find a particular beetle or something. And you stumble across an ancient Aztec culture or something, or civilization that we didn't know existed. Or these are sorts of sometimes science needs to be done just for science sake, just for the exploration's sake, and more of that.
No, absolutely. I think it has to be done. I think speculative science and just research, you never know where it's going to go. You never know where it's going to go. And it seems like all the biggest breakthroughs in science have always been like that. You never know. There's no way that Einstein could have known that looking at the speed of light and doing all those things was going to lead to the invention of the atomic bomb, for example.
Yeah.
And, if he had known, God, would he have got a big grant to have done it? How much would the American government have given him to go, here's a big grant for you to come up with a nuclear bomb? So, you just never know where it's going to go. And I think that's why it's really important that it's protected.
So that's an interesting point, because one of the views I've actually come to is that obviously I'm a scientist and I have many friends who are scientists, and I think scientists are really cool, creative people, producing a lot of cool stuff. But I also come to the view that I don't think that important decisions about whether you should make something should just be left to scientists. Because if you just take the Manhattan Project as an example, you sort of alluded to that. We're talking about Einstein a little bit. Richard Feynman talked about how after the project ended, he realized that he enjoyed it too much. And you'd start thinking about the world differently, and I've been in that exact position where I was in a job, and you're head down doing the calculations, and you're enjoying it, but you stop to think whether you should do it, whether that's the right direction. So when we open up these new avenues of science investigation, there's a possibility of uncovering things which have the potential to do enormous good to society or enormous ill to society.
This is dealt with really, really well by, funnily enough, a scientific philosopher called Nick Bostrom. Do you know Nick Bostrom? Yeah, he's recently been talking about a thing called the urn of invention, which is basically a bag full of white, grey and black balls, and you stick your hand in and you pull out a white ball, and hey, it's an invention that's really good for everyone, like penicillin. You pull out a grey ball and it's like, oh, it's a really good invention, like general relativity. It gives us lots of energy, but it also gives us a nuclear bomb. Oh, that's a bit, it's a little bit, there's a bad side and there's an upside. There could be one that you pull out and it's a black ball and it's an invention that, say, his analogy is that you pick up some sand and you can stick it in a microwave and you can blow up a city with it. And this invention now is so bad and so terrible that you've ruined the future. That the moment that you have a city destroying technology that's really cheap that anyone can make, it's like now you're in really serious trouble. And he looks at how you kind of prevent these things from happening, and looks at what you do if someone does pull out the black ball of invention. And it's a really, really fascinating paper. I mean, it basically, I think, ends up with a conclusion that you're never going to stop scientists looking into stuff, and you can never tell who's going to put their hand in and pull out a black ball of invention. But if it does happen, then we'll almost certainly have to have what he calls a turnkey dictatorship, where it's like everything's on lockdown. from that point on?
Yeah, so this is what I was alluded to earlier about I'm not sure we're mature enough yet to get out there, because I think all those issues like our ethics and morality, our governance structures, we haven't quite figured out yet, because you certainly don't want to get to a system where everyone's basically living under a dictatorship. But also, I mean, I'm a huge believer in personal liberty, but there needs to be some restraints, I feel, on what people can do if they have there's the information, the knowledge to do something, and then there's the technology or the tools to do it, right? So, I mean, talk about Manhattan Project again. One of the concerns they had when they were developing the bomb, in particular the hydrogen bomb, is that they were worried that they could set fire to the atmosphere, right? So that was considered a very low concern, but they ran the calculations theoretically, and they concluded they didn't think that was going to happen, and so they went ahead and built it anyway, right? Because I think the risk is very low. So how much of the world was involved in that decision to, what was that calculation? What was the probability? Was it 1 in a million? Was it 1 in a billion? I can't remember the calculation, but who was involved in that decision? Same with CERN. When they were building CERN, there was, because at the time, and there's still some belief that there are more than 3 spatial dimensions, and it was believed that if you look at the calculations, that there's more than 3 spatial dimensions. The Schwarzschild radius for gravitational collapse of two protons colliding at 7 tera-electron volt energy, it changes because the Planck length changes. And so actually, it was possible, in principle, if there were more than 3 spatial dimensions, for those 2 protons colliding in the particle accelerator at CERN to collide into their own Schwarzschild radius. Now, the problem is, people misunderstand black hole physics, of course, but because due to Hawking radiation, the radiation is inversely proportional to the mass, so they will radiate instantaneously, like fraction of a second, and you just get a shower of particles coming out. But there was some guys writing papers on this, and I think there was even a law case trying to stop CERN from switching on. But it's like, until we've done more work on it, it's like, well, what is the risk that you're going to create a black hole and destroy the Earth's going to disappear inside of it? There's two arguments to that. One is that they just don't understand black hole physics, because these are microscopic black holes which decay in a fraction of a second according to Hawking radiation. However, that hasn't been experimentally verified. No one's actually experimentally verified that a black hole that's microscopic will radiate inversely proportional to its mass. And the verification for that, even with macroscopic black holes, is very, tenuous. So there's that element, and then there's the other element, which is who makes these decisions to take these risks in society. I'm not trying to suggest for a moment that I think scientific experiments should be stopped. But what I am saying is that when you are dealing with the frontiers of science and knowledge, whatever it is, you have to take care, right? And that includes even going out into the universe. We don't know what's out there. We don't know what's waiting for us out there. All these discussions about METI transmitting signals out into the universe, our radio signals have been transmitted for the last century. So for principle, they're at 100 light years already, but we don't know. There might be some bad civilizations out there who, we've got lots of horror films. Aliens is a classic one, which is a brilliant film, describing those sorts of scenarios. Prometheus, where they decide to bring the pods to Earth to destroy humankind. We don't know what's out there. And therefore, even in space, I think we should tread carefully. And I feel that discussion needs to be broader than just the scientists. And I don't know if you ever saw the original Contact film based on a novel by Carl Sagan.
Yeah.
Starring I forget her name, the actress. Jodie Foster, a brilliant actress. They had this big debate in the science committee, and I think it was in Congress, where there's religious people asking her, well, do you believe in God? And so they had this big debate, and should we switch this machine on? And in the end, they switched the machine on. Of course, I don't believe her. She made the journey. But, my only point is that my own feeling is that there needs to be a broader discussion than just the physicists, because physicists are very smart people, and they're very creative. But once you get, let's say it was true that a bunch of physicists could prove a star was conscious. What's the implications of that? I'm not sure I've even thought that through. I'm just doing it because it's fun to do the calculations, and I believe it's a very low probability that they are conscious, but it's fun to do. But what's the implications of that being true? Same as when we talk about, I've been watching a beautiful documentary on trying to find an abominable, not abominable snowman, a yeti in northwestern forests of North America. Really interesting. A bunch of scientists trying to find the evidence for this thing, and evidence doesn't look strong. But what if you did find this thing? What if you did find that it's actually some offshoot hominid, goes back thousands of years, and back at the time of the Neanderthals, maybe it's Australopithecus or something. What's the implications of that? Well, we're going to put it in a zoo. That's what we're going to do if we found ones. Maybe we shouldn't, find it. I don't know.
Yeah.
So scientists are curious, and they want to know. They just want to know things, and I think sometimes it's not always wise to know.
Yeah. Oh, we're going to have to wrap it up there, Kelvin. Thanks very much. That has been super long. I'm definitely going to have to cut that in half. Thanks very much, and stay safe.
Okay.
All right, nice one. I'll tell you what. I'll give you I'll send you a link to a folder for you to drop that audio into if you have recorded it.
Okay.
And